right there, right? Here we go, right? Okay, all these things are adding up to what they added up to before. Here was an interaction that caused no change, right? They didn't exchange anything, right? And then if I hit the U key, it does it as fast as it can. Every time it does an average of of both sides, right? Are you ready for this? What's happening to the temperature of the hot stuff?
Going down.
It's getting colder. Why is that? Because it's just getting mixed up, yes? Yeah? What's happening to the temperature of the cold stuff?
Going up.
It's getting warmer. That's because it's just getting all mixed up, right? Yeah? So that's what happens. That's why heat flows from hot to cold. That's what we're talking about. And this is what conduction is on a microscopic level. Okay? So I'm going to Alt-Tab out of there. All right. Let's go back to our little presentation. We've got a couple things to go back to. Okay? Start the radiation demo. Here are things that prevent heat transfer by conduction. This is a pile jacket. I like this. I also have a layer on under my pile jacket. Usually when I'm outside in the cold. This is a real thin layer. They've got these things, they're called soft shells, right? That are like really thin pile. It's really densely woven. Anybody have one of those? They're really cool. These things are really nice because they'll keep you warm, but not quite so warm as this. Usually I'm too hot to wear that. When I'm skiing, I'll put the pile on when I stop, right? This is a down jacket. This thing packs into a space about this big due to the power of feathers. Right? I can stick it in my backpack. It weighs, half a pound or something like that, right? And then if I get hurt or something and I got to sit still for a long time, or God forbid, got to spend the night, take it, shake it out, get the feathers all fluffy, put it on, instantly warm, right? Sleeping bag's the same way, right? Here's a down vest. Doesn't need the arms. Usually you don't need the arms, So this might be enough if you're really trying to cut weight. This is polyester fill. The beauty of polyester fill is that if you're going to get wet, down is not so good in the outdoors, right? So polyfill, you can just take your polyfill sleeping bag will keep you warm when it's wet. Just wring the water out of it, shake it, spin it around your head, get inside. It'll keep you warm. Okay. Your feather, if it's full of down and it gets wet, game over. The down all wads up into a little ball, and all the shaking in the world isn't going to make it fluff up. You got to dry it out, right? Stick it in a dryer with a tennis shoe or something like that. Okay. And then this is. Not all down is created equal. This is high fill power. This is not quite as high fill power, right? Okay. So this is the thickness here is what we're talking about. And then basically all insulators just trap air. Air is a marvelous insulator if you can keep it from moving. Right? If you can keep air from moving, it's a marvelous insulator. So you just trap air. Air doesn't conduct heat very well unless it can move, right? So that's our next thing is convection. Right? Convection is just the motion of a fluid, either a gas or a liquid, right? And this is the notion, if I'm standing outside on a cold day, right, the air next to my body is warmer than the air farther from my body. There's a boundary layer of warm air. And what happens is the air, the wind just strips that away. It makes me feel colder than I would otherwise. Now, let's be silent. Be silent. What do you hear besides the music? Do you hear the whirring of many fans? The projector has a fan, the computers have a fan, the computer has a fan, the printer has a fan. Why do they have fans in them? Is that to cool them off much faster than they would be cooled off if you just allowed the normal rising of warm air versus cold air, right? Yeah, this is called forced convection. There's also natural convection, right? So let me, I could pass these guys around. They are sort of sharp. But obviously, this is a heat sink, I believe, from a Pentium 2. Yeah? Pentium 3, Pentium 4 were now many cores, right? Basically, they've got temperature sensors on these CPUs. They also have fan speed indicators. And if the fan stops, they shut down immediately because you have a matter of seconds before the CPU just fries, right? In these modern processors, right? So this is Pentium 2 could actually operate without the fan running. It was, there we have it. This is just a heat sink here. The notion here is that the heat conducts into this aluminum, which we know conducts heat pretty well, right? And then the air can go through this, and it provides a lot of surface area for the air to carry through. And this has two axes, so you can kind of look at it this way and this way. Some engineer figured out the shape of this, right? This is fluid mechanics and heat transfer, right? They tend to go hand in hand. We can pass that around. I have another demonstration of this. This is kind of fun. Natural convection then is where you heat a fluid, and the fluid rises. And the reason it doesn't really rise, there's no anti-gravity, right? The notion is that a hotter gas, for example, will expand, yes? Doesn't that mean it's less dense? Doesn't that mean it will float on the colder air? Yeah, less dense air will float on cold air. So it's just like a cork floating in. It's not that heat rises. It doesn't rise, but hot air floats on cold air. You can say that for sure, right? So let me close this. The candle's heating the air. The air is, I can feel it coming out of this. This is, kerosene lamps have glass chimneys like that. They get quite hot. And then I'm going to just make some smoke here. Back in the day, the teacher would just smoke a cigarette, you know, and be like, but this is, you know, you see the smoke going down there. Why is it going down in there? Well, it's because this thing's making the air go up this way, so it's got to pull it in that way. That's the only way I can pull it in. That's kind of fun, isn't it? And here you can see the air, the smoke is going up. You see that? A little applause for the convection thing. Woo, 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 woo. Thank you. So that is convection. This is much, much faster than conduction. And I talked about the surface layer, right? This is one of my favorite things to do is to sit in a sauna, right? And saunas, you know, are supposed to be heated up to 180 degrees. We would heat them up to like 215 degrees or something like that, right? You know, just crank them, right? You know, and then you run out of the sauna when you cannot stand being in the sauna anymore. You run out of the sauna into the frozen lake, yeah, or the very cold lake. And what you do is you run out until you're about this deep in the water, and then you go, and you sit down and you get the water up to here, yeah? Are you picturing this? And then you sit absolutely still, and you immediately heat up this little layer of water. You can't do this in a stream or a river. It has to be a still lake. You heat up this layer of water right next to you, and then you can sit there for a long time, 5 minutes, 10 minutes in this really cold water, 40-degree water, right? Because that little jacket of water is right next to you. And it just moves very slowly. Okay. Now, if a camper gets out of the sauna and jumps in right next to you and goes, "Hi, are you having fun?" They stir up the water, and you kind of yell at them. Yeah. Convection ovens have fans that blow the air through and cook stuff faster, and they claim more evenly, right? So you've got to change. If you have got a regular oven directions, you got to change it to bake cookies in a convection oven. Right, and the convection, because the air is moving, you get nice. I think it does the surface really well, right? It heats things up quickly, and it also tends not to preheat faster. And why you need to preheat, we'll talk about here. But how much time do we got? We're getting down there. All right, okay. Sauna, cold lake, car radiators. Obviously, we use convection in a car radiator. Cooling fans on computer. This is when they talk about wind chill. That's what they're talking about. And then there is a dark side to this. The Tillamook fire. If you stop at that wayside rest on the way to the beach, yeah, there is this little thing about the Tillamook burn, right? Back in the day, they didn't understand how to do logging safely. They left a lot of slash on the ground. The Tillamook burn was a firestorm. Okay, burning chunks of wood were falling on ships miles, like 30 miles out at sea. Yeah, this is a little bit unusual for a forest fire. Okay, so firestorm is when you've got a fire here, right? And what happens is, of course, the air there is floating on the cold air. The cold air is rushing in from the sides to replace the air that is floating up. Yes, okay. Now, what happens to a fire when you blow on it? Gets bigger. Usually, if it's established, it'll get bigger. Otherwise, it'll go out. Right. So the Tillamook fire is big enough that the wind coming in from the side caused it to burn hotter. Now, this is a crazy runaway positive feedback loop, right? The hotter the fire gets, the stronger the winds. The stronger the winds, the hotter the fire gets. The hotter the fire gets, the stronger the winds. The stronger the winds, the hotter the fire gets. Boom, there it was, right? It got so hot. Normal forest fires just will creep along the ground and just sort of, kill a tree here and there, right? This thing not only burned every tree all the way to the ground,